All right, well, welcome back. In the previous video, we finished up the differential equations chapter where we had a look at uh, the reduction of order and as well as the uh, homogeneous equations. So this chapter, we will be focusing on the parametric equations and polar coordinates. So basically, parametric equations, we should be a bit familiar with them back in calculus and vectors when we talked about parametric equations of a line. But now we're interested in parametric equations on different curves that are represented by curves. So, and then later on in the chapter, we'll also be talking about the polar coordinates, which we sort of touched on a little bit back in complex numbers, but haven't really went in depth about what polar coordinates are and how can we use them in calculus. So let's get started with this. So in many real life situations, when we graph the set of data, the points that we create cannot be described by a relation that is given by f of x. So in some situations, we could write x and y as coordinates separately as functions of another variable t, such as where we have x is equal to ft and y is equal to gt. So usually the t that we have here inside of these variables here, so they usually represent the um, time. So it usually represents the time of the variable of the coordinate here. So when the coordinates are expressed in this way, t is called the parameter, which is sometimes called the time, and the f and g are the parametric equations. So for example, let's say we sketch the curve that is defined by x to t, which is given by t minus t plus 1 and y is equal to t squared minus 2t. So we're going to first of all plot using the table of values first, and then we'll sketch using graph. So that means if we have x is equal to negative t plus 1, if we substitute t into the x column, what we're actually going to obtain is going to be the values for 3, 2, 1, 0, 1, and 2, right? And as for the y coordinate, well, we have y is equal to t squared minus 2t. So when we put in the t values in, what we're going to get is 15. We're going to get 8. We're going to get 3, 0, negative 1, 0, and 3. So those are those are the values that we should keep in mind when we're graphing this parametric equation here. So let's have a look at this on a graph. Okay, so let's plot our axis down. So say we have this, and we go about here. Okay, so let's say I go up the x-axis by about 5 units. So 3, 4, 5 is here. 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. 15 is over here. All right, and let's say we go about the x-axis by 5s as well. So 3, 4, 5. Here's going to be negative 4. And that's all we really need to go to in this example here. So when we plot the points that we have put in this table over here, we should be able to put the values as follows. So we had 4 and 15, so that should be over here. We also had 3 and 8, so 3 is over here, 8 is about here. 2, 3, so 2's here, and then we have 3. And then 1, 0 is going to be over here. And then we're going to have 0, negative 1, 0, negative 1, 0, and then -2, 3. So this is what we actually have. So as we could see, if we try to connect the lines, what we will actually obtain is this curve over here. So notice that, well, as the t is increasing, the x's are decreasing. So it's going to go from left to right. So these actually should be negative here. So we're going to go left, right to left on the x-axis. So the graph is essentially going in this direction now. So if you were to add arrows to the graphs, it would look something like that. And see that, well, it's following a motion to the point, this point over here. All right. So what kind of graph do we see here? Well, we will actually obtain a parabola in this case. But how can we confirm that this is actually a parabola? So let's substitute the function. So we know that, well, x here was given by -t plus 1, and y was given by t squared minus 2t. So let's say we rewrite the x coordinate, for example. So these are actually your parametric equations. So let's say if x is equal to -t plus 1, then that means t would also have to be minus 1 minus x here. And so let us substitute that into the y coordinate then. So we're going to substitute to y. And so if we substitute to yt, what we actually get is that, well, y here is going to be t, or 1 minus t squared, or 1 minus x squared, and minus 2 times 1 minus x. So if we expand this, we get 1 minus 2x plus x squared minus 2 plus 2x. And so we could cancel out some terms. The 2x cancel, and we're just left with the x squared and the constants. So what we're actually left with is x squared minus 1. And this over here is indeed a formula for a parabola, which is actually what this graph is being described as. Well, how is it different from the function that we have obtained here? Well, the thing is, the order of the points is a little bit different when we're working with parametric equations and Cartesian coordinates. So notice that, well, this time we're working in terms of t, when usually we're working with x and y's. So in this case, what we could actually say here is that, well, the order, so we say that the order of the points is different. Well, this is because as t is increasing, or as t increases, the parabola is traversing from right to left. So traversing meaning that it's traveling from right to left. Or traversed from right to left. Okay. So that's how it's different from the regular parabola that we would usually obtain. So parametric curves are also often limited to a time interval t. So say you have a particle that is moving from a time interval from A to B, that's the time it's going to take or to travel that much distance, cover that much distance, for example. So for example, in the above graph, if we use the interval t from 0 to 3 then, well, the initial point then, so when t was equal to 0, we saw that, well, x was going to be 1 and y is going to be 0. So what we have is x is equal to 1 and y is equal to 0. So that would be this point over here on the graph here. So it's this specific point there. Let me make a highlighter smaller. So it'd be this point over here that's corresponding to. And the terminal point, which is going to be called the final point, when t is equal to 3, is actually going to be what we have x is equal to -2 and y is equal to 3. So that is going to be this point over here. All right. So what is the graph that is produced by x is equal to cos of t and y is equal to sine t, for t being from 0 to 2 pi? Well, let's consider a table of values here. So just like what we did in the previous example, we're going to consider some table of values. So we're going to have our t, x, y table. And since we're going to go from 0 to 2 pi, it's best if we actually go in terms of radians here. So if we know that the initial point is 0, the final has to be 2 pi. So that means we'll consider the points pi. Let's say we go pi over 2. This is 3 pi over 2. Then the ones in between we'll consider is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so let's see what kind of values we get. So substituting all these values into cos of t, what we would actually get is the values. So what we get is 1, we get root 2 over 2, we get 0, we get negative root 2 over 2, we get -1, we get negative root 2 over 2 as well, then we get 0, then we get root 2 over 2, and then we get 1 again. So that's the values for the x coordinate. As for the y coordinate, it's similar. So we're going to actually get 0, root 2 over 2 as well, 1, root 2 over 2 still, 0, negative root 2 over 2, -1. Then we get negative root 2 over 2, and then back to 0. So let's see what happens when we plot this on the graph here. So here, what we will have is the x and y coordinate. And so let's see what we would get. So let's say that we go about here being 1. This is going to be 1 here. This is going to be -1. And this is going to be -1 here. So if we plot the points of x and y's, so this is going to be the starting point. So that's 0, 0, or 1, 0. And then you're going to go to root 2 over 2, root 2 over 2, which is approximately about here. And then we go to 1, 0. And then we go to negative root 2 over 2 to root 2 over 2. Did I go? Yeah, it should be there. And then we go to -1, 0. Negative root 2 over 2, negative root 2 over 2. Then we go to -1 here. And then we go to root 2 over 2, negative root 2 over 2. So essentially what you get, if you draw the line, you're going to go in a counterclockwise direction. Like that. So what you actually see is that we're going to get a circle, but as t is increasing, we see that the motion or the direction of the graph is going to go in a counterclockwise direction. So what we say here is that we have a circle starting at 1, 0, traversing counterclockwise 2, 1, 0. And that should be it. Okay, so let's keep on going. So we have some more examples. How are each of the following parametric curves different from the ones that we have presented above? Okay, so now this time what we actually have is sine x being the sine t coordinate, and then y being the cosine t coordinate this time. So from the above, we had that x was cos, y was sine. But let's have a look at the table of values. We should be expecting to get a circle again, but let's see. So we have our t, x, and y coordinate. And then what we get, so let's go from 0 to 2 pi still. And we're going to go from, so here's pi over 2, and 3 pi over 2. I'm going to use the 5 coordinates instead, just because it's going to be similar to the ones that we have used above. So at 0, the x coordinate will actually be 0, and this would be 1. Then we would get 1 and 0, then 0, negative 1, negative 1, 0, and then 0, 1, back to 0, 1. Okay, so on the graph, let's put this on a grid. So yeah, something like that. So we're gonna use the same number of units on the axis. So we have 5 here, 5 here, 5 here. So that's 1, 1, negative 1, negative 1. So so that means we're still gonna have these points being the root 2 over 2's about here and about here. Okay, so now we're actually going to be starting at 0, 1. When t is equal to 0, we're starting at 0, 1. So that is going to be this point over here. And so we're going to be connecting these points over here, going in a counterclockwise direction still. But as we see, this time, we're going to be starting at the point 0, 1, and we're going to be finishing at 0, 1. So it's going to go in this direction. And this point being the initial and the terminal point. So what we say here is that, well, it's a circle starting at 0, 1 and ending at 0, 1, and it's going in a counter clockwise direction. So that's the observation that we could make here. Okay. Then what about this example here then? Well, now we have cos of 2t and sine of 2t. Well, what I'm going to do is actually go back to this table over here. Going to be plotting some more points. So let's see, we have our t, we have our x, and we have our y. Okay, so once again, I'm going to go from 0 to 2 pi. And I'm going to fill in the points in between. So this is pi over 2. This is pi over 4. This is 3 pi over 4. And then this here we have 3 pi over 2, 5 pi over 2, and then 7 pi over 2. So if we fill in the x and y coordinates, what we should get is that, well, we'll get 1, 0, negative 1, 0, 1, and then 0, negative 1, 0, 1 back again. As for the y, we're going to get 0, 1, 0, negative 1, 0, 1, 0, negative 1, and back to 0. So we see that from 0 to 2 pi, or 0 to pi, we already complete one cycle here. And this second half over here is trying to complete another cycle. From the previous examples here, we see that it takes up to 2 pi, t being 2 pi, from 0 to 2 pi, it's going to take 2 pi, let's say, time in seconds maybe, to complete one revolution around the circle or travel across the circle once. But this time we're traveling across the circle twice, from 0 to 2 pi. So visually, so we have our axis. And here's our x-axis. So visually, once again, so we have these as the key points, 5, and we also have these points here. And here, yeah. So this is going to be 1, 1, -1, -1. The other ones are just going to be the root 2's. So we're starting at 1, 0, which is this point over here. When we travel through pi once, we're going to be seeing that, well, this is what we're going to get. So that's already one cycle. So that's from 0 all the way to pi. That's once around the circle here. So let me use red to indicate that this is the first time that you're traveling around the circle. And as for the second time, well, you're just going to repeat the cycle once again. So let me use a different color. Well, this is the second time you're going to go around the circle. Yeah, so this is the direction of motion. So what we could conclude here, we could make the observation that, well, it's a circle starting at 1, 0, but it's traversing twice in a counterclockwise direction. Okay, so that's the observation we can make from doing this example over here. Okay, so we had a look at 3 specific examples first by what happens when we have a look at cos t and sin t being the x and y coordinates respectively. And then we had a look at what happens when we're starting at the different point or swapping the 2 functions together, the sine and cos t. So x being the sine, y being the cos. And then we had a look at what happens if we have an extra value inside the parameter for cos and sine. Okay, so let's say we want to sketch the following as well. So both of the coordinates here are going to be sine t, x and y are both sine t. In this case, I'm just going to go ahead and use 5 coordinate points for t. And we have t, x, y given by this. Okay, so we're going to go from 0 to 2 pi as given by this interval. And so that means I'm just going to go from up pi's over 2 each time. So if we substitute the values in, well, all the x's are going to be 0 when its sine is equal to 0, which is 0, pi, and 2 pi. And same thing for y, because it's also the same function. And then we just fill in the other parts. So pi over 2 is going to be, so sine of pi over 2 is 1. This is also 1. And then these are going to be -1. Okay, so on the graph, let's see what we're working with. Okay. So let's say here's 1. Here's -1. Here's 1. This is -1. Okay, so what we have here, we're starting at 0, 0, which is going to be starting at the origin here. And then at pi over 2, it's going to travel to 1, 1. So it's going to be going to here. And then it's going to go back to 0, 0, back at the origin. And then at -1, -1 is going to be at 3 pi over 2. So it's going to be here. And then back to the origin where it started at. So if we draw the motion of the two functions here, we see that, well, it's going to go this way and then go back this way, go through this way, go to -1, -1, and then go back to this way, back to the origin. So it's going to go in the back and forth motion like this as t increases. So one observation that we can make from this graph is that, well, it's actually a line segment. So it's the line segment starting from -1 to 1, or -1, -1 to 1, 1, traversing back and forth. And you would also see that in the next example too, that, well, whenever we have cos to t as the x and y coordinates respectively, we would also see that we get a similar graph that is being produced. So let us consider the txy table again. Okay, so here we're going to go from 0 to 2 pi again. This is pi over 2, this is 3 pi over 2. So this time when we have cos of 0, both of the coordinates are going to be 1, 1. This is going to be -1, -1. This is going to be 1, 1. And then the ones involving pi over 2, 3 pi over 2 are just going to be 0. So on the same graph, I'm just going to copy this graph over here. And this is what we get. But this time we're actually going to be starting from 1, 1. So this is the starting point this time. And then we're going to go at pi over 2. This is going to be when it's pi over 2. Go back to -1, -1. Then it's going to go back to 0, 0. This is 3 pi over 2. And then back to 1, 1, which is 2 pi. So it's going to travel once back and forth in 2 pi. Let's say seconds here, for example. So this time we have the line segment from -1, -1 to 1, 1, traversing back and forth. That's what we should get here. Okay. So next, we will be having a look at calculus with parametric curves. So if we wanted to find the slope of the curve in the first example, we could actually write y as a function of x and then take the derivative. So whenever we have y as a function of x, so say y is equal to f of x, then the derivative of this is going to be dy over dx, which is f prime of x, right? But let's say if x is a function of t, for example, and y is a function of t as well, then if we let y be f of x, big F of x, so then that means we could use the chain rule. So once again, if we have y of t being equal to gt, for example, and if we have x being f of t, then that means big F, or here what we have first is, so if we let y being big F of x by the chain rule, well, that means dy divided by dt is going to be given by dy divided by dx, dx divided by dt. And so if we rearrange this, so take this, and we're going to rearrange this a little. So we're going to actually divide both sides by dx divided by dt, so that when we have dy divided by dt, we're actually just going to get, or dy divided by dx here, what we're actually going to get is dy divided by dt. This is divided by dx divided by dt. So notice that, well, on the left-hand side, this is exactly the slope of the graph when of y versus x. And these derivatives up here are the derivatives of the parametric curves of y and x, respectively. So this would be useful for the following parametric curve. So let's have a look at the example. So let's say we want to sketch the curve that is given by x, which is t squared minus 4t, and y is t plus 1. And we're going from 0 to 3 for t. So if we put this on a table, t, x, y, so we're going to go from 0 to 3. So that means we have 1 and 2 and b3. So if we put the values in, for the x coordinate, all these should be 0, -3, -4, and -3 if you do the substitution. And as for the y coordinates, what you're actually going to get is a 1, 2, 3, and 4. So on a graph, this is what you should get. So I'm going to go down this way and go through this way here. So here's the x and y axis, but we're having a look at the upper left corner here. So at t equals to 0, we have 0, 1. I'm going to go by one coordinate. 1, no, let's go. So let's go 2. This is going to be 4. And then on the x-axis, let's go by -1, -2, -3, -4. Okay, so on the graph, 0, 1 is going to be this point over here. And then we're going to go from -3, 2. So here's -3, and this is 2 over here. And then at t is equal to 2, we have -4, 3. So -4, and this is 3. And then -3, 4, once again, we have here. So this is what the graph is going to look like. And the function is going to go this way. However, notice that, well, if we want to find the slope at t is equal to 2, you see that, well, this slope is actually going to be vertical. So what does that mean? The slope is undefined then, right? So if we draw the tangent line, we want to show that this tangent is or the slope of the tangent here is undefined at t is equal to 2. So let's show that. Well, if we use the derivative definition, which is given by this over here, so we know that dy divided by dx is going to be given by the derivative of y with respect to t, dx with respect to t. So we know that dy divided by dx or dy divided by dt is going to be given by 1, and dx divided by dt is going to be given by 2t minus 4. So that means if we put it into the slope here, we're going to get 1 divided by 2t minus 4. So that means at t is equal to 2, what we're actually going to get is, well, dy divided by dt or dx evaluated at t equal to 2 is 1 divided by 2 times 2 minus 4, but we're actually just going to get 1 divided by 0. Well, that means the slope is undefined, which is exactly what we wanted to show. All right. We can also find the second derivative by using the first derivative here. Well, if dx divided by d over dx, we could also write this as d over dt, multiply that by dt divided by dx. However, or we could also then write this. Observe that, well, this over here, dt divided by dx, could actually be written as this. So we had dt dx. This is the same as saying 1 divided by dx divided by dt. And that's the general rule here. This is called the reciprocal rule for derivatives. And it's a pretty popular or unique property for in calculus that you might encounter maybe in multivariable calc. But anyways, so we could write this as d divided by dt divided by dx divided by dt. And so now when we substitute into, so we know that d squared y dx squared is the second derivative, but we could also write this as d over dx of dy divided by dx. Well, d over dx over here, we know what that is, which is given by this. So we could just go ahead and make that substitution here. And we would get d divided by dt, dy divided by dx. So this is the derivative with respect to t. And we're dividing this, oops, by dx divided by dt. And that's how you find the second derivative. So the top part of the derivative here, this is the part where we take the derivative of dy divided by dx with respect to t. And the bottom is the derivative of x with respect to t. Respect to t. Okay, so that's how you find the second derivative. Let's have a look at an example of this. So a curve is defined by x, which is equal to t squared minus t, and y is t cubed minus t. So let us determine first the equations of the tangents when t is equal to 1. So we know that, well, dy, the first derivative, dy over dx, is going to be given by dy divided by dt divided by dx divided by dt. So what that is, so the derivative of dy divided by dt is going to be 3t squared minus 1. And then this is divided by 2t minus 1. So that means at t is equal to 1, so for part A, I'll put it down here. At t is equal to 1, we're going to get dy divided by dx evaluated at t is equal to 1. So that is going to be 3 times 1 minus 1 divided by 2 times 1 minus 1. So that means you're going to get 2 divided by 1. So that means the slope at t is equal to 2 or t is equal to 1 is going to be 2. And so since we want to find the equations at the tangents, so when t is equal to 1 then that means x here, which is the point, is going to be given by 1 squared minus 1, which is 0. And y is going to be given by 1 cubed minus 1, which is also 0. So it's going to start at the origin where you're going to have a slope of 2. So that means the equation of the line then, if we're going to be using this form, which is y minus y0, m times x minus x0. So we're going to take x0 and y0 be 0, 0, which is going to be given from this part over here. And since the slope here is going to be the 2, we could just go ahead and put that in so that here we're just going to get y is equal to 2 times x, which is the equation of the tangent line. So okay, so next, let us find the points where the tangent is horizontal or vertical. So part B, the slope of tangent is horizontal whenever the derivative is equal to 0. So this is whenever dy divided by dx equals to 0. So that means from the derivative, we have 3t squared minus 1 divided by 2t minus 1, which is equal to 0. And that is when 3t squared minus 1 is equal to 0. So if you solve for t, you're actually just going to get plus or minus 1 divided by square root of 3. So those are the points when the tangents are horizontal. Now, whenever the slope of tangent, sorry, I should put is horizontal. And so if you want to find when the slope of tangent is vertical, so from the derivative, it's when the derivative does not exist. So whenever dy divided by dx does not exist. In this case, it's going to be the denominator because it's going to be a vertical asymptote. So we're going to be focusing on the denominator. So that's going to be when 2t minus 1 is equal to 0. So that means t is equal to 1/2 is when the tangent is going to be vertical. And then in part C, we want to determine when the curve is concave up or concave down. So that means we have to find the second derivative, which we could actually do by using this formula over here. So part C, we know that dy divided by dx is given by 3t squared minus 1 divided by 2t minus 1. Well, dx divided by dt, we already know that is going to be given by 2t minus 1. And d divided by dt of dy divided by dx. So that means we're taking d divided by dt of 3t squared minus 1 divided by 2t minus 1. So by the quotient rule then, this is going to be 6t times 2t minus 1 minus 3t squared minus 1 by 2. This is divided by 2t minus 1 squared. And if you simplify this, you're going to get 12t squared minus 6t minus 6t squared plus 2 divided by 2t minus 1 squared, and therefore this is equal to 6t squared minus 6t plus 2, and this is 2t minus 1 squared. And so if we combine the two now, so that means then d squared y divided by dx squared, which is the second derivative, is going to be the entire quotient here. And this is divided by 2t minus 1, in which we could actually simplify to as 6t squared minus 6t plus 2 divided by 2t minus 1 cube. Okay. So if we want to determine when the curve is going to be concave up or concave down, we have to find the critical points of the second derivative. So let me add an extra page. Okay, so we're going to let d squared y dx squared equal to 0. But note that t cannot be equal to 1/2 because it's a vertical asymptote at that point. So what we're just going to be left with is we're going to have to solve this equation here. But as it turns out, there are no real solutions. So that means this quadratic here is always going to be above the x-axis. Meaning that it's always going to be concave up. Or not always. We have to consider when it's going to be before 1/2 and 1/2. So on the number line, or actually before I write this, then, so if we consider the number line then, so let's say, so here's 1/2, and these points are going to be your interval, for example. Let's say this is negative infinity, this is infinity. So if we choose something that is going to be before 1/2, say less than 1/2, the denominator part is going to be a negative value, while the numerator is going to be a positive. So what we're actually going to get is that the curve is going to be concave down at this interval. So it's concave down when t is between negative infinity, 1/2. And then it's going to be concave up after 1/2. So as a graph, this is what we're going to get. Oops. Okay, so if we try to graph this, here's our axis. And so as a plot, it's going to look something like this. So we're going to start at 0, 0. And we also have another intercept at 1, 0, 2, 0 here. So this is going to go by 5s, 10, and then we're going to have 10 on the y-axis. And then we're going to have 2, 6, which is this point here. So it's going to look something like this. So the curve is going to go this way. Let me add another point, which is going to be 6 and slightly below here. So it's going to go here and then this way here. So it's going to go 1, 2, 3, 4, and then back to this way. That's what it's going to look like. And it's always going to be extending forward this way. So as we see between t's -1/2 or -infinity to 1/2, that's going to be this part over here. And then otherwise, it's going to go this way. Okay. So that is this example. It's quite long. But there's just some small details that we would cover in this type of example here. All right, so let's have a look at another example. So we say that a cycloid is the graph traced by a point on the edge of a rolling cylinder and whose parametric equations are given by x and y over here. So let's first find out what the equation of the tangent is at pi/3. So first, remember that we have to find the derivatives. So dx divided by d theta this time is actually going to be r times 1 minus cos theta. And then dy divided by d theta is going to be given by r times, so the one's a constant, and then we're just going to get sine theta. So we don't need the bracket. So this is the derivative of the parametric equations. Then substituting it to dy divided by dx, we're going to get, well, we had the derivative of y with respect to theta, then divided by dx divided by d theta. So that's the derivative here. So we're going to get r sine theta divided by r times 1 minus cos theta. So simplifying, we would just get sine theta divided by 1 minus cos theta. Okay, so that's the derivative. So at t is equal to, or at theta equal to pi/3, that means dy divided by dx evaluated at theta pi/3 is going to be given by sine of pi/3 divided by 1 minus cos pi/3, which is then going to be √3 divided by 2, 1 minus 1/2. So that's just going to be √3 as the slope. So as well, at theta is equal to pi/3, our x coordinate will just be r times 1 minus cos pi/3, which is just going to be r/2. And the y coordinate, or oops, my bad. This is not right. So the original function is given by x, r times pi/3 minus sine pi/3. So we're going to get r times pi/3 minus √3 divided by 2 as the x coordinate. Then the y coordinate, we're going to get r1 minus cos pi/3, which is just going to be r divided by 2. So that's the x and y coordinates here. So if you were to write this as an equation of a line, well, we know that y is equal to mx plus b, so that's √3. And then we have the x coordinate. So if I replace this by r divided by 2, and the x coordinate by r times pi over 3 minus root 3 divided by 2 plus b. You could then just go ahead and solve for b in this case, which is going to be some value over here. It's going to, if you just move 1 over, it should be that y-intercept there. But anyways, the next part is asking us, well, what are the points when the tangents are horizontal or vertical? So part B, the slope of the tangent is horizontal whenever dy divided by dx is equal to 0. Since we already have the derivative, well, all we would just have, well, is just going to be sine theta divided by 1 minus cos theta equal to 0. So that means when sine theta is equal to 0. And so that means theta is, well, sine is equal to 0 whenever theta is equal to pi over 2 or 0, pi, 2 pi, and so on up to n pi, where n is any natural number. Or actually, let me go with integer instead, because it could also be integer as well. Okay. And then, so if you want to find the slope of when it's going to be vertical, so the slope of tangent is vertical when dy divided by dx does not exist or is undefined here. So that means when 1 minus cos theta is equal to 0, well, that means when sine or when cos theta is equal to 1. And that can only happen when theta is equal to 0, 2 pi, 4 pi, and so on, up to 2n pi, where n again is any integer here. So those are the points when it's going to be horizontal and when it's going to be vertical as well. So as a graph, this is what it's going to look like. So we're going to plot this from the positive side. So this is what we're going to graph on. So at 0, 0, we're going to get this point here. Let's say at pi, so here's pi over 2 pi, 3 pi, and 2 pi's here. So here's pi, 0, 2 pi. Let's say this is going to be r. This is 2r. It's going to reach a max at this point over here. And so what it's going to look like is you're going to have a graph that looks somewhat like this. Something like that. Well, here, as we could see, at 0, well, the slope of the tangent is vertical, we said, but it's also horizontal as well. It could also be horizontal this way, it could be vertical this way. Or 2 pi as well, we could say the same thing here. And at pi, we can only have a horizontal tangent here. At pi, yeah. And the pattern would just keep on repeating itself forever. But it's also important to note that this part over here is actually just going to be a cusp, meaning is that it's not going to be vertical. So the point may exist, but the derivatives may not exist at that point over there. All right. So let's have a look at some more applications. Well, we could also determine an area under parametric curves using an integral. So let's consider the area for a regular function. So say that the area is equal to the integral from a to b of y with respect to x. Well, here we're going to be taking x to be f of t and y to be g of t as before. Well, that means dx is also the same as f prime x dt or ft dt. And so once we make the substitution, the area is also going to be from, this time we're going to let c and d, where c and d are going to be the bounds for t with respect to t this time. So the y is going to be the function gt, and then dx is going to be the f prime t dt. So this is where c and d are the bounds with respect to t. Okay, so let's see. As an example, let's find the area under one arc of the above cycloid for theta between 0 and 2 pi. So if you remember, the cycloid was given by x equal to r times theta minus sine theta. And then the y coordinate was given by r times 1 minus cos theta. So we have y, which is going to be the gt, and the x coordinate we have to find the derivative of. Luckily, we found that above, so we know that dx divided by d theta is going to be r times 1 minus cos theta. And so if we were to put this into the integral formula for area, so the integral, since theta is going to be from 0 to 2 pi, and then gt, which is given by r times 1 minus cos theta, and then dx dt, or dx is going to be then r1 minus cos theta d theta. And so I'm going to take up the r squared and then take the integral from 2 pi. I'm also going to be expanding these two terms here. So that's a perfect square trinomial. So if we expand this, what we get is 1 minus 2 cos theta plus cos squared theta d theta. So remember that cos squared theta, the integral of that is going to be, well, we could also write this as 1/2 plus 1/2 cos 2 theta. So we could write it like that. So let's go ahead. So we have 1 minus 2 cos theta plus 1/2 plus 1/2 cos 2 theta with respect to d theta. All right, so that means r squared, if we combine everything, the integral of this is going to give you 3/2 theta minus 2 sine theta plus 1/4 sine 2 theta. And this is evaluated from 0 to 2 pi. But if we put theta into each of these signs, they're both going to be equal to 0 for both 2 pi and 0. So those are just going to be gone. Don't have to worry about them. And what we're left with is just going to be this 3 divided by 2 theta. So once we make the substitution, we're actually just going to get 3 pi r squared, which is the area of the cycloid between 0 and 2 pi. And so from the graph up here, this is what it's going to look like. That's the area here. Okay, so after areas, we could also find the arc lengths of the parametric curves. So remember that the arc length of a parametric curve was given by L, which is the integral from a to b of the square root of 1 plus dy divided by dx, whole thing squared, dx. And then, well, since dy divided by dx here is also the same as saying dy divided by dt, dx divided by dt, and dx here is also the same as saying dx divided by dt, dt, making these two substitutions, we could say that, well, the integral from a to b times, or the integral from a to b of the square root of 1 plus dy divided by dt, dx divided by dt, whole thing squared, dx divided by dt by dt. And I'm also going to be changing the bounds for a and b because they're with respect to x right now. So let's call them c and d. And I'm also going to bring the dx divided by dt inside of the square root. Why? Well, if I do that, that means I have to write like this. And we also have 1 plus dy dt dx dt squared. And this is now with respect to dt. So when I do distribute this, what I'm just going to get is that, well, dx divided by dt is going to be from this part. And then the second one, I could just have the dy divided by dt squared because this is going to cancel with this. So the length then, arc length, is just going to be given by the integral from c to d of dx divided by dt squared plus dy divided by dt squared dt. All right. So let's have a look at an example of this. So let us find the circumference of a circle given by x is equal to cos theta, y sine theta. These should be thetas from 0 to 2 pi. Okay. So the length, well, we could just go ahead and use the formula. Well, dx divided by dt is going to be given by negative sine theta, and dy divided by dt is going to be given by cos theta. So that means if we square them, dt squared, this is going to be sine squared theta, and dy divided by dt, whole thing squared, this is going to give me cos squared theta. And so if I put this into the length formula then, so from 0 to 2 pi, so we have sine squared theta plus cos squared theta. And this is d theta. What we see now, inside the square root is going to give us 1 because sine squared plus cos squared is always going to give you 1. So that means we're integrating this. And if you can compute this easily, you should just get 2 pi. So 2 pi here, 2 pi is the circumference of a circle with radius 1. So that's a quick, short part on the arc length for parametric curves. And one more. application is that we could also have a look at the surface area. So the surface area can also be found similarly. So remember that the surface area is given by 2 pi times the integral from a to b of y square root of 1 plus dy divided by dx squared divided by dx. However, one thing that we have found already is this part over here. Remember that this entire expression, or this part over here, is exactly this up here. So if we could make that quick substitution, well, what we're just going to have is that 2 pi, the integral from c to d, the y here, remember, is also gt, so that's just going to give you gt times the square root of dx divided by dt squared, dy divided by dt squared, divided by, and that's good. So and then dt there. So that's the surface area form. And a quick example of this is that, well, if we want to find the surface area of a sphere by rotating the parametric curve given by x and y between 0 and pi. So these should, it's with respect to t, so it's okay. So s here, or let's find dx divided by dt, which is once again negative sine t, and dy divided by dt is cos t. And putting that in, squaring them, we know that's going to be sine squared plus cos squared. So s here from 0 to pi of sine t, that's the square root of negative sine t squared plus cos t squared dt. So that is the integral from 0 to pi of sine t dt. Because the inside of this part is just going to equal to 1, so don't really have to worry much about that one. And then the integral of sine t is going to be negative cos t from 0 to pi. But that's also the same as saying cos of t between pi and 0. And that should give you just 2, which is exactly, or no, I forgot the 2 pi out here. So that's 2 pi, 2 pi. So 2 by 2 pi then would actually just give you 4 pi, which is the surface area of the sphere with radius 1. So surface area of a sphere with radius 1. Okay, so that is going to wrap things up for this lesson over here. So in conclusion, we talked about the parametric curves. We had a look at some sketching problems of parametric curves, try to see the difference between them. We also had a look at some calculus techniques that we could use to describe parametric curves. So we found when the slopes of the tangents are going to be horizontal or vertical. And we also had a look at the second derivative of the parametric curves. And then we also had a look at a couple of examples of this one, for example. And then we also had a look at some other applications of parametric curves in calculus involving areas, arc lengths, and surface area. So that's going to wrap things up for this lesson for today. So if you have any questions, just feel free to leave them in the comments down below. And I'll see you guys in the next lesson.